Hello everyone, welcome to the lecture on transaction management and concurrency control. And in this lecture, we shall learn about database transactions and their properties, what concurrency control is and the role it plays in maintaining the database's integrity, what locking methods are and how they work. Moreover, we shall also be looking at how stamping methods are used for concurrency control, how optimistic methods are used for concurrency control, and finally, we will look at how database recovery management is used to maintain data integrity. What is a transaction? In database terms, a transaction is any action that reads from and or writes to a database. A transaction is a logical unit of work that must be entirely completed or entirely aborted. No intermediate states are acceptable. A successful transaction changes the database from one consistent state to another. A consistent database state is one in which all data integrity constraints are satisfied. To ensure consistency of the database, every transaction must begin with the database in a known consistent state. If the database is not in a consistent state, the transaction will yield an inconsistent database that violates its integrity and business rules. For that reason, subject to limitations discussed later, all transactions are controlled and executed by the database management system to guarantee database integrity. Most real-world database transactions are formed by two or more database requests. A database request is the equivalent of a single SQL statement in an application, program, or transaction. For example, if a transaction is composed of two update statements and one insert statement, the transaction uses three database requests. In turn, each database request generates several input or output operations that read from or write to a physical storage media. Clearly, improper or incomplete transactions can have a devastating effect on database integrity. Some database management systems, especially the relational variety, provides means by which the user can define enforceable constraints based on business rules. Other integrity rules, such as those governing referential and entity integrity, are enforced automatically by the database management system when the table structures are properly defined, thereby letting the DBMS validate some transactions. For example, if a transaction inserts a new customer number into a customer table and the customer number being inserted already exists, the database management system will end the transaction with an error code to indicate a violation of the primary key integrity rule. Each individual transaction must display atomicity, consistency, isolation, and durability. These properties are sometimes referred to as the acid tests. In addition, when executing multiple transactions, the database management system must schedule the concurrent execution of the transactions operations. The schedule of such transactions operations must exhibit the property of serializability. Let's look briefly at each of these properties. Atomicity requires that all operations of a transaction be completed. If not, the transaction is aborted. If a transaction T1 has 4 SQL requests, all 4 requests must be successfully completed. Otherwise, the entire transaction is aborted. In other words, a transaction is treated as a single indivisible logical unit of work. Consistency indicates the permanence of the database's consistent state. A transaction takes a database from one consistent state to another consistent state. When a transaction is completed, the database must be in a consistent state. If any of the transaction parts violates an integrity constraint, the entire transaction is aborted. Isolation means that data used during the execution of a transaction cannot be used by a second transaction until the first one is completed. In other words, if a transaction T1 is being executed and is using the data item, let's say X, that data item cannot be accessed by any other transaction until transaction 1 ends. This property is particularly useful in multi-user database environments because several users can access and update the database at the same time. Durability ensures that once transaction changes are done, they cannot be undone or lost, even in the event of a system failure. Serializability ensures that the schedule of the concurrent execution of the transaction yields consistent results. This property is important in multi-user and distributed databases where multiple transactions are likely to be executed concurrently. Naturally, if only a single transaction is executed, serializability is not an issue. A single user database system automatically ensures serializability and isolation of the database because only one transaction is executed at a time. The atomicity, consistency, and durability of transactions must be guaranteed by the single user database management systems. Multi-user databases are typically subject to multiple concurrent transactions. Therefore, the multi-user database management system must implement controls to ensure serializability and isolation of transactions, in addition to atomicity and durability, to guard the database's consistency and integrity. For example, if several concurrent transactions are executed over the same data set, and the second transaction updates the database before the first transaction is finished, the isolation properties is violated and the database is no longer consistent. The database management system must change the transactions by using concurrency control techniques to avoid such undesirable situations. The American National Standards Institute, or ANSI, has defined standards that govern SQL database transactions. Transaction support is provided by two SQL statements, commit and rollback. The ANSI standards require that when a transaction sequence is initiated by a user or an application program, the sequence must continue through all succeeding SQL statements until one of the following four events occurs. A commitment statement is reached in which case all changes are permanently recorded within the database. The commit statement automatically ends the SQL transaction. A rollback statement is reached in which case all changes are aborted and the database is rolled back to its previous consistent state. The end of a program is successfully reached, in which case all changes are permanently recorded within the database. The action is equivalent to commit. The program is abnormally terminated, in which case the changes made in the database are aborted and the database is rolled back to its previous consistent state. This action is equivalent to rollback. The transaction log. A database management system uses a transaction log to keep track of all transactions that update the database. The information stored in this log is used by database management systems for a recovery requirement triggered by a rollback statement. A program's abnormal termination or a system failure, such as a network discrepancy or a disk crash. Some relational database management systems use the transaction log to recover a database forward to a currently consistent state. After a server failure, for example, Oracle automatically rolls back uncommitted transactions and rolls forward transactions that are committed but not yet written to the physical database. This behavior is required for transactional correctness and is typical of any transactional database management system. While the database management system executes transactions that modify the database, it also automatically updates the transaction log. The transaction log stores a record for the beginning of the transaction. Each transaction components, the type of operation being performed, for example, update, delete, or insert, the names of the objects affected by the transaction, example, the name of the table, the before and after values for the fields being updated, pointers to the previous and next transaction log entries for the same transaction, the ending commit of the transaction. Although using a transaction log increases the processing overhead of a database management system, the ability to restore a corrupted database is worth more the price. Concurrency control. The coordination of the simultaneous execution of transactions in a multi-user database system is known as concurrency control. The objective of concurrency control is to ensure the serializability of transactions in a multi-user database environment. Concurrency control is important because the simultaneous execution of transactions over a shared database can create several data integrity and consistency problems. The three main problems are lost updates, uncommitted data, and inconsistent retrievals. Lost updates. The lost update problem occurs when two concurrent transactions, example T1 and T2, are updating the same data element and one of the updates is lost or overwritten by the other transaction. Uncommitted data. The phenomenon of uncommitted data occurs when two transactions, let's say T1 and T2, are executed concurrently and the first transaction is rolled back after the second transaction has already accessed the uncommitted data, thus violating the isolation property of transactions. Inconsistent retrievals. Inconsistent retrievals occur when a transaction accesses data before and after another transaction's finishing work with such data. For example, an inconsistent retrieval would occur if transaction T1 calculated some summary or aggregate function over a set of data while another transaction was updating the same data. The problem is that the transaction might read some data before they are changed and some dates and other data after they are changed, thereby yielding inconsistent results. The scheduler. The scheduler is a special database management system process that establishes the order in which the operations within concurrent transactions are executed. The scheduler interleaves the execution of database operations to ensure serializability and isolation of transactions. To determine the appropriate order, the scheduler bases its actions on concurrency control algorithms such as locking or timestamping methods, which are explained in the next sections. However, it is important to understand that not all transactions are serializable. The database management system requires what transactions are, the database management system determines what transactions are serializable and proceeds to interleave the execution of the transactions operations. Generally, transactions that are not serializable are executed on a first-come, first-served basis by the database management system. The scheduler's main job is to create a serializable schedule of a transaction's operations. The serializable schedule is a schedule of transaction operations in which the interleaved execution of transactions yields the same results as if the transactions were executed in serial order, that is, one after the other. The scheduler also makes the computer's central processing unit and storage systems more efficient. If there are no way to schedule the execution of transactions, all transactions would be executed on a first-come, first-served basis. The problem with the approach is that process time is wasted when the CPU waits for a read or write operation to finish, thereby losing several CPU cycles. In short, first-come, first-served scheduling tends to yield unacceptable response times within the multi-user database management system environment. Thereby, some other scheduling method is needed to improve the efficiency of the overall system. Additionally, the scheduler facilitates data isolation to ensure that two transactions do not update the same data element at the same time. Concurrency control with locking methods. A lock guarantees exclusive use of a data item to a concurrent transaction. In other words, transaction T2 does not have access to data item that is concurrently used by transaction T1. A transaction acquires a lock prior to access of data. The lock is released when the transaction is completed so that another transaction can lock the data item for its exclusive use. This series of locking actions assume that there is a likelihood of concurrent transactions attempting to manipulate the same data item at the same time. The use of locks based on assumption that conflict between transactions is likely to occur is often referred to as pessimistic locking. Recall from the earlier discussions that data consistency cannot be guaranteed during a transaction. The database might be in a temporary inconsistent state when several updates are executed. Therefore, locks are required to prevent another transaction from reading inconsistent data. Most multi-user database management systems automatically initiate and enforce locking procedures. All lock information is managed by a lock manager, which is responsible for assigning and policing the locks used by the transactions. Lock granularity. Lock granularity indicates the level of lock use. Locking can take place at the following levels: database, table, page, row, or even field attribute. Database level. In a database level lock, the entire database is locked, thus preventing the use of any tables in a database by transaction T2 while transaction T1 is being executed. This level of locking is good for batch processes, but it is unsuitable for multi-user database management systems. You can imagine how slow the data access would be if thousands of transactions had to wait for previous transactions to be completed before the next one could reserve the entire database. In a table level lock, the entire table is locked, preventing access to any row by transactions T2 while transaction T1 is using the table. If a transaction requires access to several tables, each table may be locked. However, two transactions can access the same database as long as they access different tables. Page level. In a page level lock, The database management system will lock an entire disk page. A disk page or page is the equivalent of a disk block, which can be described as directly addressable section of a disk. A page has a fixed size such as 4K, 8K, or even a 16K. A row level lock is much less restrictive than the locks discussed earlier. The database management system allows concurrent transactions to access different rows of the same table even when the rows are located on the same page. Although the row-level locking approach improves the availability of data, its management requires high overhead because a lock exists for each row in a table of the database involved in a conflicting transaction. Modern database management systems automatically escalate a lock from a row level to a page level lock when the database application session requires multiple locks on the same page. The field level lock allows concurrent transactions to access the same row as long as they require the use of different fields within that row. Although field level locking clearly yields the most flexible multi-user data access, it is rarely implemented in database management systems because it requires an extremely high level of computer overhead and because the row level lock is much more useful in practice. Lock types. A binary lock has only two states, locked or unlocked. If an object that is a binary table, page, or row is locked by a transaction, no other transaction can use that object. If an object is unlocked, any transaction can lock the object for its use. Every database operation requires that the affected object be locked. As a rule, a transaction must unlock the object after its termination. Therefore, every transaction requires a lock and unlock operation for each data item that is accessed. Such operations are automatically managed and scheduled by the database management system. The user does not need to be concerned about locking or unlocking data items. The labels shared and exclusive indicate the nature of the lock. An exclusive lock exists when access is reserved specifically for the transaction that locked the object. The exclusive lock must be used when the potential for conflicts exists. A shared lock exists when concurrent transactions are granted read access on the basis of a common lock. A shared lock produces no conflict as long as all the concurrent transactions are read-only. A shared lock is issued when a transaction wants to read data from the database and no exclusive lock is held on that data item. An exclusive lock is issued when a transaction wants to update a data item and no locks are concurrently on it. Deadlocks. A deadlock occurs when two transactions wait indefinitely for each other to unlock data. In a real-world database management system, many more transactions can be executed simultaneously, thereby increasing the probability of generating deadlocks. Note that deadlocks are possible only when one of the transactions wants to obtain an exclusive lock on a data item. No deadlock condition can exist among shared locks. The three basic techniques to control deadlocks are prevention, detection, and avoidance. Let's look at them broadly. Deadlock prevention is when a transaction requesting a new lock is aborted when there is the possibility that a deadlock can occur. If the transaction is aborted, all transactions made by this transaction are rolled back and all locks obtained by the transactions are released. The transaction is then rescheduled for execution. Deadlock prevention works because it avoids the conditions that lead to deadlocking. Deadlock detection. The database management system periodically tests the database for deadlocks. If a deadlock is found, one of the transactions, the victim, is aborted and rolled back and restarted, and the other transaction continues. Deadlock avoidance. The transaction must obtain all of the locks it needs before it can be executed. This technique avoids the rolling back of conflicting transactions by requiring that locks be obtained in succession. However, the serial lock assignment is required in deadlock avoidance increases action response times. The choice of the best deadlock control method to use depends on the database environment. For example, if the probability of deadlocks is low, deadlock detection is recommended. However, if the probability of deadlock is high, deadlock prevention is recommended. If response time is not high on the system's priority list, deadlock avoidance might be employed. All current database management systems support deadlock detection in transactional databases, while some database management systems use a blend of prevention and avoidance techniques for other types of data, such as data warehouse or XML data. Concurrency control with time stamping methods. The time stamping approach to scheduling concurrent transaction assigns a global unique time to stamp to each transaction. This timestamp value produces an explicit order in which transactions are submitted to the database management system. Timestamps must have two properties, uniqueness and monotonicity. Uniqueness ensures that no equal timestamp values can exist, and monotonicity ensures that timestamp values always increase. All database operations within the same transaction must have the same timestamp. The database management system executes conflicting operations in timestamp order, thereby ensuring serializability of the transactions. If two transactions conflict, one is stopped, rollback, rescheduled, and assigned a new timestamp value. The disadvantage of timestamping approach is that each value stored in the database requires two additional timestamp fields, one for the last time the field was read and one for the last update. Timestamping thus increases memory needs and the database's processing overhead. Timestamping demands a lot of system resources because many transactions might have to be stopped, rescheduled, and restamped. In this section, we shall learn about two schemes used to decide which transaction is rolled back and which transactions continues executing, with the use of wait or die and wound or wait scheme. Using the wait or die scheme, if the transactions requesting the lock is the older of the two transactions, it will wait until the other transaction is completed and the locks are released. If the transaction requesting the lock is the younger of the two transactions, it will die or roll back and is rescheduled using the same time stamp. In short, in the wait or die scheme, the older transaction waits for the younger to complete and release its locks. In the wound or wait scheme, if the transaction requesting the lock is the older of the two transactions, it will preempt or wound the younger transaction by rolling it back. Transaction 1 reempts transaction 2 when transaction 1 rolls back transaction 2. The younger preempted transaction is rescheduled using the same timestamp. If the transaction requesting the lock is the younger of the two transactions, it will wait until the other transaction is completed and the locks are released. In short, in the wound or wait scheme, the older transaction rolls back the younger transaction and reschedules it. Concurrency control with optimistic methods. The optimistic approach is based on the assumption that the majority of the database operations do not conflict. The optimistic approach requires neither locking nor timestamping techniques. Instead, a transaction is executed without restrictions until it is committed. Using an optimistic approach, each transaction moves through 2 or 3 phases referred to as read, validation, and write. During the read phase, the transaction reads the database, executes the needed computations, and makes the updates to a private copy of the database values. All update operations of the transactions are recorded in a temporary update file, which is not accessed by the remaining transactions. During the validation phase, the transaction is validated to ensure that the changes made will not affect the integrity and consistency of the database. If the validation test is positive, the transaction goes to the write phase. If the validation test is negative, the transaction is restarted and the changes are discarded. During the write phase, the changes are permanently applied to the database. The optimistic approach is acceptable for most read or query database systems that require few update transactions. In a heavily used database management system environment, the management of deadlocks, their prevention and detection constitutes an important database management system function. The DBMS will use one or more of the techniques discussed here as well as variations on those techniques. However, the deadlock is sometimes worse than the disease that locks are supposed to cure. Therefore, it may be necessary to employ database recovery techniques to restore the database to a consistent state. Database recovery management. Database recovery restores a database from a given state, usually inconsistent to a previously consistent state. Recovery techniques are based on the atomic transaction property. All portions of the transactions must be treated as a single logical unit of work in which all operations are applied and completed to produce a consistent database. If, for some reason, any transaction operation cannot be completed, the transaction must be aborted and any changes to the database must be rolled back. In short, transaction recovery reverses all the changes that the transaction made to the database before the transaction was aborted. Database transaction recovery uses data in the transaction log to recover a database from an inconsistent state to a consistent state. Before continuing, let's examine 4 important concepts that affect the recovery process. The write-ahead log protocol ensures that transaction logs are always written before any transaction data are actually updated. This protocol ensures that in case of a failure, the database can later be recovered to a consistent state using the data in the transaction log. Redundant transaction logs ensures that a physical disk failure will not impair the database management system's ability to recover data. Database buffers are temporary storage areas in primary memory used to speed up disk operations. To improve processing time, the database management system software reads the data from the physical disk and stores a copy of it on a buffer in primary memory. When a transaction updates data, it actually updates the copy of the data in the buffer because the process is much faster than accessing the physical disk every time. Later on, all buffers that contain updated data are written to a physical disk during a single operation, thereby saving significant processing time. Database checkpoints are operations in which the database management systems writes all of its updated buffers to disk. While this is happening, the database management system does not execute any other requests. A checkpoint operation is also registered in the transaction log. As a result of this operation, the physical database and the transaction log will be in sync. This synchronization is required because update operations update the copy of the data in the buffers and not in the physical database. Checkpoints are automatically scheduled by the database management systems several times per hour. Transaction recovery continued. The database recovery process involves bringing the database to a consistent state after a failure. Transaction recovery procedures generally make use of deferred write and write-through techniques. When the recovery procedure uses a deferred write technique, also called a deferred update, the transaction operations do not immediately update the physical database. Instead, only the transaction log is updated. The database is physically updated only after the transaction reaches its commit point using information from the log transaction. If the transaction aborts before it reaches the committed point, no changes need to be made to the database because the database was never updated. The recovery process for all started and committed transactions follows these steps. Identify the last checkpoint in the transaction log. This is the time transactions data was physically saved to the disk. 2, for a transaction that started and was committed before the last checkpoint, nothing needs to be done because the data are already saved. 3, for a transaction that performed a commit operation after the last checkpoint, the database management system uses the transaction log records to redo the transaction and to update the database using the after values in the transaction log. The changes are made in ascending order from the oldest to the newest. For any transaction that had a rollback operation after the last checkpoint or that was left active with neither a commit nor a rollback before the failure occurred, nothing needs to be done because the database was never updated. When the recovery procedure uses a write-through technique, the database is immediately updated by transaction operations during the transaction's execution, even before the transaction reaches its committed point. If a transaction aborts before it reaches its commit point, a rollback or undo operation needs to be done to restore the database to a consistent state. In that case, the rollback operation will use the transaction log before values. The recovery process follows these steps. Identify the last checkpoint in the transaction log. This is the last time transaction data were physically saved to the disk. 2, for a transaction that started and was committed before the last checkpoint, nothing needs to be done because the data was already saved. 3, for a transaction that was committed after the last checkpoint, the database management system redoes the transaction using the after values of the transaction log. Changes are applied in ascending order from oldest to newest. For any transaction that had a rollback operation after the last checkpoint or that was left active before the failure occurred, the database management system uses the transaction log records to roll back or undo the operations using the before values in the transaction log. Changes are applied in reverse order from newest to the oldest. Summary. Transaction, it is a sequence of database operations that access database. Logical unit of work, no portion of transactions can exist by itself. The 5 main properties of transactions are atomicity, consistency, isolation, durability, and serializability. Commit saves changes to the disk. Rollback restores previous database states. SQL transactions are formed by several SQL statements or database requests. A transaction log basically keeps track of all transactions that modifies a database. Concurrency control coordinates the simultaneous execution of transactions. A scheduler establishes order in which concurrent transaction operations are executed. A lock in databases guarantee unique access to data item by transactions. There are two types of locks: binary locks and shared or exclusive locks. Serializability of schedules is guaranteed through the use of two-phase locking. Deadlock, when two or more transactions wait indefinitely for each other to release lock. Three deadlock control techniques include prevention, detection, and avoidance. Timestamping methods assign unique item stamp to each transaction. Schedules execution of conflicting transactions in timestamp order. Optimistic methods assume the majority of database transactions do not conflict. Transactions are executed concurrently using private copies of the data. Database recovery restores database from given state to previous consistent state. And this finishes our lecture on transactions and concurrency controls. Thank you for listening, everyone. Goodbye.